Hello everybody and welcome to another episode of the oscilloscope comparison that I'm doing. And today I'm going to post the fifth episode in those series. And some people have been asking me about the missing episodes, but there's nothing of a mystery here really. I'm not always posting these episodes in the order of the original table I've been showing, because the actual order depends a bit on the project that I'm doing. But I am intending to make like the full series what has been originally been put in that table, so stay tuned for that. I also want to thank people for the large amount of feedback I've been receiving, mostly via the EEV blog. This feedback really allows me to turn into new investigations, to improve and find out things about these devices. So keep on posting your feedback, and also thanks for the many positive comments I've received on this series. Having that said, let's turn to today's topic. We're going to talk about tools. And I'm going to talk about the tools that we really use on a daily basis of this instrument that become essential to many of us. And I'm going to focus today on cursor tools, on measurement tools. I'm going to focus on the digital voltmeters that are at least supported by two devices that I'm looking at today. And I'm going to look at frequency counters. So first I want to talk about the cursors. And actually there is not so much difference between the cursor implementation of these three devices, so I don't want to spend too much of your time on that, and I'm not going to put up several separate videos for all of them. On the screenshots here you see all the three devices with cursors being active, so they all offer the same basic functionality. We have manual cursor lines, either two horizontal lines for time, two vertical lines for voltage, combination of voltage of horizontal and vertical, at least for the RTB and the SDS. All of these devices can also couple the X1 and the X2 and the Y1 and Y2, so you move both of them at the same time as a kind of a window along your waveform. Also, all of the devices offer the tracking of waveforms, and that's actually what you see on the screenshot right now. So he's tracking the amplitude at a given point in the waveform. All these three devices, at least in their current version, also offer you to track two different waveforms, so there can be channel 1 and channel 2, and they are all kind of showing the same type of basic measurements along the time scale, along the vertical scale. There are a couple of small differences. The Roden and Swartz, for example, can show you delta Y over delta X, so you can see that as a rise time, it's expressed in kilovolts per second. The SDS in turn can show 1 over delta X, so that's a frequency basically in megahertz if you wish. So there's some small differences. The Keysight has a dedicated button, a dial for the cursor, that's nice too. But otherwise, there are no big differences. These are all powerful, well implemented cursor functions. The only thing that is different and that I would care about is actually one of the tricks that the SDS had in its sleeve, but we actually will talk about that when we talk about the measurement position, because it's linked to that. Focusing next on the measurement mode of these three scopes, I think we first should look briefly at the type of measurements that these devices support. And actually there are quite a lot of them. It ranges between about 30 different types of measurement for the RTB and the DSOX, all the way up to 51 different types of measurements for the SDS. So they do have quite a lot in common. So in terms of horizontal measurements, they all do standard stuff like frequency, period, duty cycle, rise time, fall time. And on the horizontal scale there are a couple of specific measurements only supported by one or two of the devices. They're shown here, and I particularly like the burst width that the RTB offers here. Now, all of these devices also offer some horizontal measurement between channels, so you select two different channels and can look, for example, at delays. All of them can show you the phase delay, phase difference between two channels, and all of them have different options to look at the delay for digital channels. So it's basically looking at rising edge or falling edge. They're all kind of different exactly in what you can do there. So we see there's a different number of combinations that you can make there. Now, importantly, on the vertical scale, we have a number of measurements, and there's of course the common one like peak, top and base, and the amplitude, the difference between top and base. There's the mean, same as the average. There's root mean square for the AC component only, overshoot type of measurement that's offered by all the devices. There's also some specific functionalities offered only by one or two devices, and I particularly like the crest factor, and I will mention that a little bit later on as well when I'm going to demonstrate the devices. There is counting. All the devices support counting of positive and negative pulses, and some of them go a little bit further in counting type of measures, including the Keysight that also offer a bit rate. And then the SDS is the only one that has a number of area type of measurement where surfaces are being calculated. And I think it is actually expressed in Weber. It's a quite interesting thing in itself, but you can find more information in the background document. Let's now take a look at our oscilloscope and see how the measurement functions are being implemented here. And to do so, I have set up 4 simple signals. I got first of all here a sine wave, and it's AM modulated. We got parts with a high amplitude and we got parts with a lower amplitude. Secondly, I've prepared a square wave, and that square wave is actually the one that has been used to do the AM modulation of the sine wave signal. I got a bit more complex waveform. This is a Bessel function, and this is interesting because it has particular features in terms of relation between peak values and average values. And finally, I prepared an arbitrary waveform signal, which is a stair signal. And as you can see, all these 4 are in sync with each other. And I'll be feeding the same signal in each of the 3 oscilloscopes, and I'll also put them all at the same time basis and vertical scale. So the time basis here is 5 milliseconds. And you will also see here that we got 1, 2, 3, 4, 5, 6 instances of this particular high amplitude sine wave here. On the other devices we're only going to see 5. They're all set to 5 milliseconds per division, but since the RTB has 12 divisions horizontal versus 10 divisions of the other device, we get to see a little bit more here. Now, let's go and take a look at the measurement functions that we got over here. And the easiest way to go there is to go to measurement, and then we can select what is called a measurement place, and we can select something that it is gonna do there. And what it's gonna do here, that comes from this menu, and I think it's actually pretty well laid out. From each of these little pictures here, even without words, it's rather clear how it's implemented and what you can expect here. There's going to be one big exception to that, but I'm going to talk about that in detail in a moment. But the measurement function in general, I think, are very clearly implemented here. Now, I'm going to leave this measurement position where it is. It's RMS here, and I'm going to activate it, and we're going to see it here. I'm going to turn all the statistics for a moment. Here down at the bottom, this is the RMS value for the whole screen. And likewise, I can turn on other positions, and I will do that right now. So this is position 2, position 3. There's no way to globally activate all the measurement positions that were earlier used. You have to turn them on one by one. It's not a big issue really, but I would have preferred to have a global on-off type of function here. So we got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 measurement positions here. Actually, that's fairly new. That's since firmware 2.4. Before that, there were only 4 measurement positions. I really welcomed that it went from 4 to 6, because I'm using this function quite a lot myself, and I really enjoy to be able to read multiple things out of the 4 channels at the same time. By the way, like all the other devices, these measurements can be done on regular channels, but also on reference channel, math channels, etc. They're very flexible, but that's the case for all the devices that I'm talking about here. Now, what we also see here, that the And let me first explain what the different things we're seeing. We're seeing the root mean square, and that's for the whole waveform. We see the root mean square value for a single cycle, and I'm going to talk about that in much greater detail in a moment. We see for the square wave, we see this is green, so it is a square wave here. We see voltage stop and voltage base. So this is basically the plateau value, so not the peak values positive and negative. There are separate ways to measure that, but these are kind of the base, so it does not include any overshoot here. So I'm interested here, or I can see from here with voltage stop, voltage base, basically how much these how this signal is exactly that I'm using for the modulation of that AM waveform. I'm showing also the frequency of the third waveform here. This is a function that all of these devices have. I'm also showing the crest factor. Only RTB has a crest function, and it's quite useful, particularly for those that are interested in power systems and power analysis, because the crest factor is something that is often necessary to know of, for example, when you set the measurement range of devices, so they're able to deal both with the peaks but also to pick up the signals that you're interested in. This is the only device actually that offers the crest function here. I also note that the voltages here are shown in quite a bit of precision, with 3 digits after the period. Remember, this is a 10-bit ADC in this device, so it can afford to show you the measurements a little bit more precisely. The other devices are going to show less digits because they're only 8-bit oscilloscopes, so basically you cannot measure that precisely. Now we're going to move on to the statistics function here. Like all the devices, there's a statistic function, and roughly speaking, these statistic functions are fairly similar. Activated here again with the push of a button. And what we see here is the statistics screen, how we can make it smaller and bigger the way that we like. It's presented in a very clear way. I would say we got all the type of things that you would expect. And we see the measurement value, the current value there, the minimum of that particular measurement, the maximum over the time that we'll be looking at, the mean, standard deviation, and the number of counts over which these statistics are measured. We can reset the statistics here. We can also reset it basically from a button on the device. Actually, all the devices have a hardware button that, among other things, can reset the statistics screens. We see also the speed of the wave count. I'll get back to that in much more detail in a moment when I talk of one of the other devices. And as the only device here, we got a save function, so we can save the statistics output to a memory drive, and it's saved as a comma-separated value file for those that find that useful to use. Now, there's one final thing I want to visit in a bit more detail here at the RTB. And now let me just globally turn off all the statistics. We can do that. This is just to stop the statistics, but if we globally stop all the measurement, they all go away. Well, actually, I didn't want them all to go away, so let me just revise that by putting back on the first and the second measurement position, because that's what I'm interested in right now. So I got the first and the second here. Again, let me... Yeah, so we got them down here. So we see root mean square for the whole wave, so that is basically average for the root mean square measurement it has been doing over both the high and the low amplitude area, and we see the root mean square for a particular cycle. Now the big question, of course, is which cycle is exactly measured, and to know this we can look at the manual of the RTB oscilloscope, and there it says that it measured the value, the voltage of the leftmost signal period. And actually, if you read in other parts in the manual where they talk about the leftmost signal period, they also explain it's leftmost, it's the most leftmost displayed section of the waveform on the selected channel. So what is that? I would say it's over here. It's what we see all the way left on the waveform here. And actually, I don't think that's a strange thought, because that's exactly the way this same function has been implemented on the SDS by Siglent. So I expect it to pick up this value over here. So in order to check if that is right, I can just move around the waveform using the time-based settings, I'm going here and I would expect it picks up this waveform here and the value will be high. No way, it stays at 0.9 millivolts only. And I expect it to be bigger than this, which is the average. I would expect it to go close to 2 or something. And if I go to a low area here on the back, no, it's still at 0.9. So this isn't doing what the manual says that this function is doing, I think. I tried to dig into that a little bit, and I think I came a little bit closer to what the oscilloscope is actually doing. And to demonstrate that, I actually that's why I have the ARP function over here. I could also have used the ramp, but in this case I use the ARP function. And I'm now going to trigger on the ARP function. So right now I was just triggering here on this block wave, so it always triggers nicely and stable. Now I'm going to trigger down here, so let me change my trigger source. This button here gets blue, this all gets blue, also tells me that this is selected. Now it's actually picking one of the plateaus over here. Now, let me now also play a little bit with the trigger settings. I'm going to the highest plateau over here. Do we have a stable trigger? Yes, we do. We got a little light here. The trigger is here, somewhere on these high forms. And look at that. Yes, now we got 2.1 volts. Now I'm moving the trigger lower in the plateau. So let me go somewhere over here. The trigger is here. That also corresponds to a lower part of this AM waveform. And yes, now the AM waveform is 0.9. And if I bring the trigger back to corresponding to high part in the plateau and here is back at 2. So actually the position that it is measuring the wave of in terms of this cycle thing is related to the trigger. So if you want to go somewhere else, you have to create another channel that would allow you to trigger at another position over here. That's not only kind of inconvenient, but is not in correspondence, I believe, with the manual. And I don't get any visual feedback except this type of experiments, what I'm actually doing. I would really like to be able to see what exactly is being measured over here. Now, I should stress that this is kind of the only time in the RTB manual I came across such an inconsistency, because generally speaking, the RTB manual is very concise and very complete in the information it offers. But at this particular function, in the measurement function, I'm a little bit at odds. So that is certainly a criticism of me of this oscilloscope. Otherwise, measurement functions work smooth, work very well. You have to select them one by one, so we will see in a moment there are kind of better ways of doing so. But altogether, I mean, it works satisfactory on the RTB. I'm turning now to the Siglent oscilloscope, and we're also going to explore here how the measurement function exactly is implemented. I'm feeding it with exactly the same signals as we have seen here before, and here we get to see 1, 2, 3, 4, 5 of these waves, because as I explained, we got 10 divisions instead of 12 divisions here. Now let's move right away to the measurement mode. Easiest way to do that is to click the measurement button, and then we get to the measurement menu. I'll just take it away for a second, and I'm going to see 1, 2, 3, 4, 5 different measurement positions in this particular mode. I've chosen roughly the same thing, so I'm choosing the root mean square and the root mean square for a cycle. I'm choosing these two voltages, and you see here the voltages are shown in less precision because we're dealing with an 8-bit analog digital converter. And I'm showing here the mean of this signal over here. In order to select any particular measurement setting, we go here. We also get to see pictures. I think the pictures are kind of less self-explanatory what they are doing exactly, and there are actually some of them which actually left me in quite a bit of doubt what they actually mean. Let me check out one of them if I see a particular one here that I would like to talk about. No, let's just leave it at that for a moment. There is a bit of an explanation here. The thing being that once you want to see the explanation and you click something, it's gone. And then you actually have to remember where it is and go back to that menu, actually see the explanation you were asking for. So it's helpful to have a little bit additional text, but not really in this way, I would say, where the text actually disappears when you when you need it most. But as we will see, we're going to explore some pretty nice functions here of this device, so let's not stick here too long. So we had 5 measurement positions. So what's the exciting thing about these 5 positions? Actually, we can move to another display mode, the M2 mode, and in the M2 mode we actually get to see 12 measurement positions at the same time. And that is really so much more than all the other devices I've been looking at. So for those that want to do many simultaneous type of measurements here, it is really excellent to get many of them at the same time. I will return to the more extensive measurement mode, but for a moment I'm going back here because then we can go and explore the statistics menu. And actually here we go, we get to see the statistics. We roughly get to see the same type of things as we were seeing before. So we get to see the actual value, we get to see the mean value, minimum, maximum, peak, I think that's an extra, standard deviation as we saw before, and count. And as you might see here, the count is pretty slow. Now I've been investigating this a little bit for the 3 different devices, and I'm going to show you right now on the screen what the count measurement is. So what I did is actually feed only one signal into the device, which is either a 1 kilohertz or a 10 megahertz sine wave. I'm going to activate a RMS measurement for that and the statistics, and that's all. Everything else is turned off. All the devices are in the same state. And then we see that the SDS is going to be very slow at 3 measurements per second in that setting. The RTB is already like 5 or 6 times as fast, and the Keysight is blazing fast in doing that. And then if we move to a 10 megahertz signal, all the devices get a bit faster, but also there the Siglent is way slower than all the other devices. So if you really need to have this type of statistics and know a little bit about what moment things are getting stable or what's the standard deviation you have, then you have to be rather patient here on the Siglent. But apart from that, we do get a number of really very nice functions here. And let me move a little bit to these functions. Let's go and take a look at it. We can go to the statistics settings and we can get to see an histogram. And now it gets to get very exciting here. So this histogram is actually show us something of the statistical distribution here, and actually I'm here in the mean for signal 3. I'm gonna go to signal 4 because I think that's going to be a little bit more. So I've changed this here. It takes a little bit while to get that. Yes, it's done here. So why are these type of histograms very useful? Yeah, we get to see really the distribution, the RMS distribution. We see a bit of a kind of a normal distribution. These are measurement issues, so they're going to be around a normal distribution around a value. This is also a bit like that. We see the top and the base value actually don't show any variance at all. Of course, we can already know that as well from the low standard deviation, but here you get much more insight here. And we get to see the mean here, and that's the mean actually of the stairs function that I choose here, actually is a discrete thing. So it only takes upon a number of discrete values. And we can even make it bigger. So we click here. And then we get to see that indeed these are only a number of different discrete values. Some of them have came along a little bit more often than others. But if we would let it stay like for a long time, then it probably would even out. He would have seen each of the different measurements probably as often as the others. So having these ones, and I'm actually going to look here as well. So here we see much more like a normal distribution, which more indicates a type of measurement thing. The standard deviation is fairly small, so we're not seeing here a big deviation. But it's interesting to see how these type of values are being distributed, and the same thing here, it's always the same low value, so we don't get to see any variance. So I think this function is particularly useful to have a histogram function here of all the measurement values at once. I don't think we get to see that, or I know that we don't get to see that in the mode with 12 measurements, but we do get to see it for 5 measurements, including one that we can choose to make larger. So I think that is a super useful function here. We don't see a possibility to save the values that we got right here in the statistic section. We do get a way of turning all the measurement globally on and off just by this button. So now they're all gone. I can make the screen a little bit bigger, and now they're all back and gone and back. So I wish the Roden and Schwartz actually would do it that way. But we're not done yet. Actually, I'm going to explore further as well which part of the waveform this device is measuring. And again, for this reason, I have selected the root mean square for the whole thing and the root mean square for a single cycle only. It's getting a little bit cluttering here, so I'm actually going to turn the statistics off, like I did on the RTB. I have to press a little bit harder. Statistics off. Oh, well, that's the statistic menu, sorry for that. The on and off are always the opposite way around than I expect them to be. Yeah. So here we see the two values I'm interested in. 1.5 volt, and that's over the whole thingy. And I see now a low measurement of 3.07. So where is that 3.07 based on? Like Roden and Schwartz, Siglent explains, is the most leftmost wave that we see here on the screen. So here let's move it around with the time base, and let's move a bigger one here. Yes, 2.1. And if I'm moving away from it again, let me get it. 300 millivolts. So yes, this seems to be a confirmation that it is actually measuring the way that the manual explains it. And we can get more than this type of indirect type of explanation because there's actually a very nice feature being built in here that I want to take a look at. Now if we go to cursors, and in cursor mode we can choose measure, and actually it's already activated because I'm coming now from the measure mode, and I can choose my measurement item, and that's the cycle RMS I'm interested in. And look at that, what we get to see. It's actually showing us exactly which waveform is, which part of the waveform is the basis for the measurement. So that's really perfect. I can play around here, I can play with the time-based settings, and I can go here, and we'll take a little moment, and look at that, he's picking exactly the thing I'm interested in. Can I move this window along? Yes. So you see that? He's showing us exactly what he is using for his basis, and also here, and again, yeah, can move a little bit around, and it moves with me, and it takes a moment to stabilize, and exactly doing what we want. It's a little bit cluttered here. I wish, for example, that they would keep on the shadow in this menu instead of being transparent. We can also go to following, but then it's even more cluttered. I'm not very crazy about this view here, and this is the one that you cannot drag around. But regardless the things with the presentation here, I think this is really an excellent function, and actually it has this type of function on many of these different management. It will basically tell you about all this type of measurements, what they are based on. So here, well, we don't need to see it's left right because we know that because of the function, but we get to see the RMS function, and that it's for the whole thing, so it's higher than the low amplitude, and it's smaller than the big amplitude. Also with all types of measurement functions related to time, etc. Yes, this is really excellent. We really get to see here exactly which part of the waveform is being measured here. I'm going to turn the cursors off because we're not done yet. There are further ways basically to work on exactly which part of the waveform we're looking at. Maybe I should mention that the time base is not a super good idea for this, because Siglent, and I find that a little bit weird, does not have a fine position for the time base. So I can make the time base like big steps, 1 to 5 steps, but I cannot click it and then do small steps like almost any other device that I've ever worked with. So that means that you cannot basically make a wave as big as you want it to be exactly from the left to the right of the screen and then do the measurement on it. But that's not something to mourn about, because it's actually something much better, at least when it comes specifically to this measurement function. Let me go and look at that. I think it's on the tools, and no, it's not on the tools, it's on the configuration gate. Yeah, and do you see what we get there? we get to see gate values between which the device is measuring. So if I want to move them around, I have to press the gate button, and suppose I want to pick exactly that part over here. So I'm having that gate button, I'm having that gate button here, and you see I can select exactly the area that I would like the device to look at, and then also measure that for the other waveforms here. So in that sense, I think this is really also an excellent function that is missing on the other devices, and that really allows you to have much more control over the exact measurements that this device is doing. So let's turn that off, the gate function. We've seen what it does. It also had threshold, which is like what is exactly the middle value if we, for example, do count measurements or things like a duty cycle. And we can also do something like upper and lower when we want to know something about rise time, for example. Is it 10% to 90% or 20 to 80%, etc. All the other devices, by the way, offer this as well. So this is not very differentiating here. Still a couple of more things here that we haven't seen yet that I would like to look at. We also got a couple of tools here which are called trend and tracks. And trend is right over here, and we can select a particular waveform, and we get to see a trend window for that particular waveform. Actually, I will be doing the trend for the mean here at the bottom. So that's that value over here. So what we get to see here is that over time we go and see the trend of that. Now, this is obviously much more useful if I have a very slowly fluctuating signal, that it changes like every 5 seconds, or it drifts a little bit or something like that. So this demonstration is not particularly useful here, but I think you do get the point about this this trend thing here. And it's a window that you can move around. We can close it again, and there's also a track function. The track function is more limited in terms of which measurement functions are supported. In this case, it's only the cycle RMS one that I can select. And here we get to see a track window. We can move it around. It's a floating window. We can decide on the skills and manual. To be very honest, I haven't studied this one in great detail. I don't know exactly how it works. There's also no information at all in the manual about it, so that would have made things a little bit easier. So I might further want to investigate it and see what other people have done with it. I haven't found much use of it yet, but it might be a very useful function once I get to master it a little bit better. And I hope at some point Siglent will also update its manual to describe these type of function, and anyway to make the manual much more complete in terms of what it's describing. So I'm going away from this now. I think we covered most of the measurement functions. There are a couple of more things, and you'll find it in the background document, particularly also to the M12 mode with more measurement position and how that is laying out on the screen. Yeah, we can actually still go and take a quick look there. So we go to the... Actually, you could call it M5 or M12. I think that would have been a little bit more obvious. So here we can simply, just choose the number of position that we would like to get and see. And we could actually put it like at 5 or so. And so we get the maximum screen size. Yeah, that we would like to have here. So we don't get to select here histograms. I think that would be hard to do anyway for so many measurement positions at the same time. But I really do appreciate the amount of measurements that we can get into. Actually, we also got, for example, duty cycle here, and the fall time here, and the rise time for 10 to 90% for the square wave I got here. Yeah, I got so many measurement positions. I can kind of do this all at the same time. So summing this up, I think the Siglent is really excellent when it comes to measuring. It really has a couple of functions, including the histograms and including really showing exactly using the cursors to show which part of the waveform it's measuring. That makes it measurement functions very, very useful. The only thing that leaves a little bit to be desired, I think, is the update speed of the statistics here. That is very low compared to the other instruments. So it depends on what you're doing and the frequency of the type of signals that you're analyzing. You might wish that to be much higher. But overall, I think the Siglent has by far the best measurement mode. Now let's also take a look at the implementation of measurement at the Keysight. And of course we know this is a rather different device, also in the way that the user interface works like. Let's do it. And of course I'm showing you the same signals that go into the device right now. It got like a 10 division horizontal screen, so we get to see 5 of these measurements, always using the same time base as the previous ones. Now, measurement positions are basically in the menu over here, and we get to see 4 measurement positions in total. And one way we get to see right away, and that it shares with the Siglent here, is you get visible feedback. I'm getting feedback already here on this particular function here, so that is probably the peak that it chose by default, and to see where it is taking it from. So that's already a nice thing to see. I'm going to clear all the existing measurements for a second, so I'm getting back to this menu, and I'm going to show you how I can add measurements here to the menu. So I'm going to try to add the same type of measurements here. So my source is channel 1, the type, and then I can actually go and choose here, and I wanted RMS for the first one, so I get to see RMS full screen, and I'm interested in what that exactly means. Then I should be pressing this. No, that is wrong. I go here, I'm pressing this button for a couple of seconds, and I get to see a complete on-screen explanation of that particular function, which is nicely done, I think. Now, if I want to add other functions, it is not always that intuitive, but I go to this button here, and I would like to look at one cycle here, DC. It doesn't show one cycle, it shows n cycles, and I'll show you in a second what that exactly means in this context. I add a measurement, and then you see it's added here as the second one over here. I can add a third one, so I was doing source number 2, and I was doing the top and the base. So I'm going to do the same things as I did on previous devices. It's added now, and I'm going to do the base. So now we got 4 position fill. If I now add another one, then this one will be deleted, and the new one will be added as position number 4. So it's a kind of first in, first out type of mechanism. It takes a little bit of playing around with it to getting used to doing it. I get to see the values here. We can see the voltage with only one thing after the digit, but I think it kind of makes sense. This is only a 8-bit ADC. So we got the statistics here as well. Actually, the statistics were added relatively recently by means of a firmware update, but they're there now. We can turn the statistics screen on. We're getting to see it over here. We can make it transparent, but that's usually not such a good choice. I like to see it over in a way over here. We can reset the statistics like all the other devices. We also have a way to reset the statistics with a button right on the screen. Well, here's actually the soft button that we got over here. See also the incredible fast count, and this also depends a little bit what you're feeding into it and what you're measuring, but this device is super fast in collecting samples for its statistics, and sometimes you see, yeah, it goes to K, the scale, and sometimes you see it at 16K or 30K, and that many statistics it has been collecting here. So the statistics part work pretty well. Yet there's one point of little annoyance. If you have the measurement function and the statistics on, for example, and you would use the digital voltmeter, what is actually happening here is that all the time the one window is jumping over the other window, as if these have been different software teams working over it. And sometimes you have this issue on the Keysight that 2 menus are conflicting with one another. Now I'm turning to the review of the digital voltmeters and the frequency counters. I'll do this combined per device that we're going to look at, and we start again with the RTB. And in terms of the signals I'm looking at right now, looking at the situation which I just emulated, which is going to be like 4 power rails, like 2 positive power rails at 8 volts and 5 volts, and especially the 8 volts got quite a bit of noise in it, the 5 volts a little bit less, and also the corresponding negative power rails 5 volts and minus 8 volts. I've chosen this example because of recent work I was doing on repairing my Tektronix AM503 current probe amp that was having a number of power supply problems there. In the end it turned out to be some wet tantalum capacitors, which is no fun to find suitable replacements. But I was facing a little bit of situation like this. But right now I'm emulating this with some function generators. And using these signals, I'll take a closer look at the digital voltmeters that the various scopes have on offer, as well as their frequency measurement. So on the RTB, we can activate the digital voltmeter with a little icon here. We can also do it via an app. And what we get to see is 4 measurement positions. We can move it around on the screen. So we got 4 measurement positions, and each of these positions can be assigned to any of the channels and can be assigned to 3 different types of measurements here. Let's go and take a look at it. I'll put it, I'm moving now. Moving a little bit down to the back. So if I click on any of them, I will get into the settings menu. So meter position number 1, source, and the colors here nicely correspond, like with most of the devices, with the channel that is selected. And I can choose here basically from direct current. I can make a root mean square RMS measurement, which includes both the AC and the DC component. And you can also take out the DC component and just look at the AC component. So you can do that for each of the different channels here. Now, so we see now the DC component I've selected for all the different channels, and I see my 8 volt power rails positive and negative, and my minus and my 5 volt power rails negative and positive. Right now I got channel 1 selected on the oscilloscope. We can see that also because of the colors of the buttons here. And if we overload the channel, so that makes twice as big, we do get a nice overload warning on that channel as well down here at the channel information. So that's a useful way of implementing this. Thinking further about the implementation, how does this work within the device? Now, if we look at the user manual, then we find that the digital voltmeter captures input data with the selected vertical sensitivity and basic accuracy of the ADC. So using the same analog digital converters as it's used for the regular traces, which is not much of a surprise in this type of device. However, as explained, it's also independent from the capture settings and the post-processing, and measurements are based on a measurement interval that ensures reliable results over the defined frequency range, as the manual says. And actually that frequency range is indicated here, it's 1 MHz. So this is independent of any settings of the acquisition system in terms of the time base, etc. And it can measure anything within the at least AC signals up to 1 MHz bandwidth. That also means, and we just saw that when I was playing with the buttons, that the scaling takes place via the channels. So we have to make sure that our signals are, of course, scaled within the range of the ADC here. This also brings in another issue that I would like to discuss with you, because as you will have noticed, I'm looking here at DC measurements. However, now if we go to a particular channel, I'm going to channel 1, and I'm going to move that channel to AC, what we actually get to see is that the meter gets fooled. It is showing 100 millivolt, close to 0. Maybe I should do some self-alignment today on the oscilloscope, but it goes basically back to 0, which is of course understandable because it's using the ADC and it's using basically the coupling that is selected for the channel, and I'm now choosing AC coupling. And even if there would have been an entirely separate type of measurement type of thing, then also the question if that will be before or after the channel coupling here. So that is not an issue in itself. My issue is that this is not noted here and the user is not warned. So you might be mistakenly thinking that this particular channel has a DC component of only 100 millivolts, while in reality it still really has the 8 volts REL. And I would very much have preferred, and I will show you in a moment how that works in one of the other devices, that the RTB would have noted it and would have notified us, either taking away that channel or perhaps changing this to an AC measurement, which is still possible here, but we do not get any warning right here. Now I'm setting the channel back to DC here. The RTB also offers a frequency counter, and it is implemented separately from the digital voltmeter that we just looked at, and you can go there via the apps menu and choosing counter here. Now it just says counter. Actually, before firmware version 2.000 this said trigger counter, and it could only show you the trigger frequency, but it has been upgraded since then. One of the few things that has not been reflected in the most recent manual. Normally kind of all the new features in firmware are properly represented in the new version of the manual RTB. This is one of the only, I think, that has been forgotten there. So I get basically a floating window. The floating window shows me both the frequency and the time period for it. And here we can actually select between the different channels here. I'm on the timeout, and the trigger itself. And of course, if the trigger is connected to an external trigger, then all of these 5 values could be different. It's a rather basic type of thing, but it works perfectly fine. It's a trigger or channel frequency counter at work. Moving now to the Siglent SDS2000x Plus series. I can be a little bit shorter because this device does not have a digital voltmeter in the sense that the other devices have it, so we're not going to talk about that. It does have a frequency meter, however, a frequency counter, and we can take a look at it by going to analysis and go to counter. We get into a menu here and we can choose between frequency and period. Later I'll get to the other option here, so I'm going to stick here with frequency. We can select different sources 1 to 4 analog channels. We cannot select trigger here, but there's nothing wrong about that because the trigger frequency is already always shown on the screen over here, so you don't need, of course, a separate type of frequency counter for that. So if we take the frequency counter and we can drag it around on the screen, we can set a level. We got statistics here. The other devices don't have that, so we get to see rather basic statistics. The statistics update rate is fairly low. It's only once every 2 seconds. The update rate of the frequency counter itself should be considerably faster. I think the manual says that it's like 100 updates per second or so. Only the statistics are much slower. Now, there's one other feature here which is rather unique, at least not present on the other instrument here, and that is the totalizer. I mean, the period, I think you get the point here. We just get the period shown. I would rather have shown it at the same time as the frequency, but they made it into a separate menu you need to activate. However, the totalizer is kind of interesting. The totalizer allows you to count unique type of events, and typically this will be rising or falling edges that happen within a certain period or from a certain start point on. And so what is that start point? We can define it here in the totalizer via the gate settings. So what is happening here basically is that you can either choose a level or you can trigger the gate itself on some edges. And you can, if you wish, to use another channel for that. So I can use channel 2 in order to turn on the gate for frequency measurements at channel 1. So this allows you to do a number of functions that usually would be for dedicated type of frequency counters here. But this is possible with the Siglent scope. It is important to note, however, that the frequency counter function, I'm going back here now to the regular frequency counter function, is independent of the channel that is selected for trigger. However, the trigger needs to be correctly set in level, otherwise it's not going to pick up. Where we saw that the other devices kind of do this automatically, here you do have to take care via the level setting that you select the right level. So it can be done on a channel that is not certain for trigger at the moment, but you do have to set the trigger level properly for that channel. And it does also work with channels that are selected for the serial trigger option in the device. And finally, we're also going to look at the Keysight here for its digital voltmeter. And some people have commented on the chat that, and were asking me like, why are you looking at the Keysight in the first place? It's such a different instrument, no way it can keep up with these recent oscilloscopes. Yes, it's an entirely different instrument, but really I like it. It's a joy to use, and it's just a whole different way of working with it, a different setting. Some people recently call this like the Fluke 87 of multimeters, and yeah, in a sense, you know, that's it. It works entirely different, but it's, I think, a satisfying device to work on. But anyway, we're going to focus on the digital voltmeters and the frequency counter on the device. So let's go and take a look. Again, going to look here at these power REL signals, 8 volts, 5 volts, 5 volts, -5 and -8, and I put a little bit of noise on there. And now let's go to the voltmeter, and here this voltmeter is under the analyze function. I would have to go here to the digital voltmeter and select it, and what we get to see here is a window popping up. We're going to see a 3-digit voltmeter here, and it's nice, like this 7-segment display thing. It really reminds you of an actual digital meter. And it's not only shown in the display here, but it's also shown here on the bottom. And I'll show you in a moment that this actually disappears when you leave the menu, the bigger window. But it's always going to be present here down on the bottom. So what type of possibilities we have here? We can of course select the source here. And the source changes nicely again with the color, like most of the scopes here. We can choose the type of measurement, and here we got DC, including an RMS component, and RMS component but only taking the AC and taking out the DC. And we got frequency separately. I'll look at that in a moment. I'm going to put it back on DC here. So basically the measurement modes that we got here are identical to what we've seen in the RTB. Now, also this device basically takes its measurements after the ADC, like the R&S, and I guess that's the common implementation in oscilloscopes. But also in this case, the manual explains us that these measurements are, and that's how they write it, asynchronous from the oscilloscope's acquisition system and are always acquiring. And so it's the same thing as with Roden and Swart. It uses the ADC but does not use any of the time-based setting. It just does so independently. And in this case, actually, it also has a range much more limited than the RTB, from 20 Hz to 100 kHz, so not to a full megahertz. But it will give you warnings if the AC component has frequencies that are above this 100 kHz and it's not properly calculating this anymore. Now, I just explained you that signals here coming in via the ADC, so it's going to depend also on the channel setting. So if I'm turning the channel on, this is still slightly within the picture, but here you see also a warning that I'm clipped right now and he cannot properly measure this anymore. Going back here. We also get to see here a little bar, and that white bar is telling us the measurement extreme over the last 3 seconds or so. Well, I got a signal that's not fluctuating, so we're not seeing a lot here. But the blue bar basically shows the last measurement, and the white bar shows measurement that occurred in the last 3 seconds, mimicking a little bit how some digital multimeters works, and it's a bit of a, yeah, it's a useful function. Now, in terms of the measurement range, there are a couple of things more to note with this device in order to use it properly. So as I just explained, we can basically select here via the analog channel. However, we also have an auto range function that we see here. And actually, if I will be going to channel number 2 here, then the auto range activates itself. Why it's not available? Why was it not available on channel 1? Well, the auto range is not available for channels that are selected for trigger, for whatever technical reasons. If a channel is not selected for trigger, then the auto range basically is available. We can turn it on, and actually we see now turning it to maximum sensitivity, but this overrides the channel setting. So if you selected any channel setting for that particular menu, then you have to be aware, and this is now for the second green channel. I'll just be turning it back now. You see, and I cannot even turn it back because every time I try to change the setting is being overridden by that automatic range setting. So I do have to go back to the Analyze menu, turn auto range on, then I can go to a particular channel and get it back. And it also kind of messed up my my position setting here. I think it was somewhere over here. Yeah. So I mean, there's nothing inherently wrong with it. This is an automatic type of measurement range that can be useful, also because you can select channels that are currently not activated, but you have to be very aware how this kind of interacts with the channel setting, and you might get different result of behavior than you're aware of if you don't understand this way of functioning very well in the device. And I almost forgot to show you how this particular meter deals with the channel coupling settings. Because as I explained also, this device basically uses the ADC for its measurement. So now I'm showing again the measurement for channel 1, which is the power rail of 8 volts. That all look fine. And the channel is DC coupled, so that's why we can measure it. Now what happens if we actually couple the channel to AC, then the menu disappears. This is a thing with the Siglent, that these menus disappear, with the Keysight, sorry, that these menus disappear all the time when they're not activated. Now I change my channel to AC coupling, and I see it going down here. And what happens here, very nice, the meter automatically changes to AC because he realizes that a DC measurement is actually not possible. And the moment I return my channel to DC, the meter jumps back to DC. So this is really the way I'd like to see this implemented, and this is also the way I would like to see it implemented on the Roden and Schwartz, that the user actually get informed properly, or even turn it off altogether. That's fine with me too, but don't try to show a DC value when the actual channel is AC coupled and cannot show such a value. The frequency meter on the Keysight is combined with the digital voltmeter we already were taking a look at. And actually, if we activate the digital voltmeter from here, we actually always get to see the frequency down here. So this is the frequency I set for my sine wave, 1.2345 kilohertz. So we get a 7-digit frequency meter. It's always shown here. Now, one thing with the whole digital voltmeter and frequency meter is that if you leave this particular menu, it's disappearing altogether. So you only get to see the reading over here. So let's go back to the meter here. So if we would permanently like to see the frequency, then we should select frequency as a source here. And what we actually be getting the frequency here, which is also going to be shown down here in the left bottom of the instrument. It's a rather basic frequency meter, but it behaves as one would expect it to behave. So we're coming to the end of today's episode, and I know the episodes are fairly long, but I really want to get into the real detail with these devices, not to leave it as something more superfluous. So, is there a winner today? And yeah, I think so. And it's going to be the Siglent today. If you look at the cursors, all the devices are kind of similar. They're all powerful. If you look at measurements, Siglent really has a number of things that the others do not have. And most in particular that we can exactly see which part of the waveform it's analyzing for particular measurement functions, have here the link that it has to the cursor system, and also that it gives us the histogram, which is very useful. You ask any statistician, if you really want to understand your data, you don't want only the descriptive statistic, but you really want some graphic representation of the waveform, so you really get more insights into the distribution here. On the side of the digital voltmeters, the Roden and Schwartz and the Siglent have a bit more to offer. But altogether for me, I think it's the measurement part that really makes the Siglent the better implementation device that we've been looking at today. But that again might change, of course, for the next episodes when we're going to look at different functionalities. So stay tuned.